right. Your exams are being graded, so hopefully we can get those graded this week. Working on it. So I'll get the grades posted as soon as I can. Current topic is principal components. So we spent a good bit of the course already on multivariate modeling and inference so far. So we've talked about how to do inference on a mean vector or a difference of mean vectors. So that's inference. That's p-values and confidence intervals. We're going to take a little time for the next week or two or three to do exploratory things. Inference is confident statements about a population using data, typically confidence intervals, p-values. Exploratory data analysis is making pictures, computing summary statistics. So it's more like just looking at the data, being a detective with the data, less about formal statistical inference with p-values and confidence intervals. But it's a very important part of doing data analysis because, especially with a multivariate data set, it's not easy to just look at your data. You have an Excel spreadsheet, it's not easy to visualize it. Things like principal component analysis and cluster analysis are exploratory techniques that are very valuable for just learning the big picture of your data set. What are the major features and patterns and relationships in your data? We're going to start with principal components. So I posted a video on Friday that goes through the first chunk of the slides. Let me just briefly review. So in principal components, here's the problem set up. We have a collection of variables, p variables. And with a sample of data, we would have n observations of each one of these. So my data set would be n by p. Each column is a numeric variable. And our goal is to kind of visualize these variables in as simple a form as possible. One way to visualize a collection of variables is to force them into a smaller dimensional representation. If I have 10-dimensional data, I can't possibly make a scatter plot to look at the data. But if there's a sensible way to cram all 10 variables down to just 2, or maybe just 1, or even 3, then it'd be a lot easier to make some kind of picture. If, for example, I could take 10 numeric variables and without losing much information at all, transform them into just 2 variables, then I could make a scatter plot and look at the relationships and look at the outliers and where typical values are and stuff like that. So the goal of principal components, PCA, is to reduce the dimensionality of the data, to go from p variables down to a smaller number. And if you think about it, there's lots of ways that you could do that. You could say, I have 10 variables, and in order to reduce the dimensionality, I'm only going to pick 3 of them to represent the whole data set. That would reduce the dimensionality from 10 to 3. And you could dream up lots of other ways to go from 10 to a smaller number. The principal component method goes about it in a specific way. So PCA, we are searching for new variables that are linear combinations of our original variables. So a linear combination of our p variables. A linear combination, we could write that like a vector of constants transpose x. That would be a constant times variable 1 plus a different constant times variable 2, and so on. So a linear combination of the p variables turns the p variables into just one variable. Because I take all p of them, I add them up with these coefficients, and now I have just a single number instead of p numbers. What we're going to do is look for a collection of these. So I'm going to put a 1 in front of all these a coefficients to indicate this is the first linear combination. But let's also look for another one. And dot, 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 we're going to find as many linear combinations as there are variables. That might sound counterintuitive because the way I motivated this was to take p variables and force them into a smaller number. What Principal Components does is find in a specific way p linear combinations of the variables. But what we're going to do with those is say the first one, the A1 linear combination, is the one that best represents the data. If you were to take all p variables and force them down into just one variable, this is the best way to do it in terms of maintaining the same information content. A2 will be the next best linear combination, and we'll be able to quantify how much of the information is preserved with each of these. So we start with p variables, and we're going to discover p linear combinations, but then we're only going to take the first handful of them. Suppose we have 10 variables, p is equal to 10. We're going to do this Principal Components trick to find 10 linear combinations that I can use to equivalently represent the data. But then we're going to say, you know, if you take just the first 2 of these, maybe you are able to capture 90% of the story that was in the entire data set. You can explain 90% of the variation with the first 2, suppose. Then we could proceed for exploratory purposes with replacing the 10 variables with just the 2 discovered ones. 10-dimensional data, but now I can make a 2-dimensional scatter plot of the data. It's not the complete data, but it's like 90% or some high percentage of the information content has been preserved. And the short story is the first principal component. Each of those linear combinations is called a principal component. So each variable that's a linear combination we discover, we're going to call it a principal component. The first principal component is what we called A1 transpose X. Out of all linear combinations of the p variables, which one is best at preserving the total information content? So the task of Principal Components is to find A1 such that the variance of A1 transpose X is maximized. the principal component idea is heavy on the concept of variability, variation, because variation means information. In the lecture video, I talked about these baseball data. And we had, for a bunch of baseball players, some career statistics, like what was your batting average over the course of your career, how many hits did you have, how many home runs, and all of that. And if we wanted to take all those players and represent them with just a single variable, the task is about spreading them out as much as possible. We have a bunch of players. Each player has a hit variable, a home runs, a batting average, all these numeric variables. So I can spread the players out perfectly if I use all those variables. Joe Johnson had such and such batting average, this many hits, this many home runs. In terms of explaining the data, I've got sufficient information with all those numeric variables to do it. I can separate everybody from everybody else. If I'm going to transform all those numeric variables into just one, a sensible way to go about it is to try to find the linear combination that spreads the players out as much as possible. A bad idea would be to replace the P numeric variables with a new variable that does not change. Instead of 1,000 players and everybody's got their own hits and home runs and everything, I could replace all those variables with the number 2.5 for every single player. I did a linear combination and I end up with the number 2.5 for every single player. If I did that, I lost all the information in the data. I can't tell one player from the other at all. There's no information in the data. So we want to not do that. We want to get as close as possible to the information content in the entire data set. So I predict that it's a little bit counterintuitive that we're saying my goal is to find the linear combination of my variables that maximizes the variance. But maximizing the variance means spreading out the players or the individuals as much as possible. And that's the idea of preserving information content. I want to take my P variables and cram them down into just one right now. My criterion for doing that is I want the resulting data to be as much of the story as possible. And it turns out that there's a solution. The solution to this math problem is that A1 should equal E1. The first eigenvector of the covariance matrix. So let me just show you the slides for a second to tie what I just said to the slides. The first chunk of the slides presents a theoretical discussion of the population parameters themselves. So this is before we actually see data. We just have x1 through xp are the numeric variables we're going to observe. There is a covariance matrix in the population. That's a population parameter, sigma. Sigma has eigenvalues. We'll call them lambdas. Remember, there's p lambdas. If there's p variables, there's p eigenvalue eigenvector combinations or pairs. Then the first principal component is the linear combination A1 transpose X that has the biggest variance. we impose a constraint in order to reduce redundancy. We impose a constraint that my linear combinations have to have length 1. This subject 2 says that A1, whatever it is, it has to have length 1. And then the result is that the ith principal component is that EI transpose X, where EI is the ith eigenvector of S, or sigma. The best way to take your P variables and cram them down to one variable in terms of preserving information content is to do eigenvector, is to use the coefficients of the first eigenvector for a linear combination. And it turns out that the variance of that principal component, the best variance we could get out of all linear combinations, its variance is the eigenvalue that goes with that eigenvector. So the best linear combination, the first principal component, is the linear combination where the coefficients of the combination come from the eigenvector. And then we have that the variance of A1 transpose X is lambda 1. Then we go to the second principal component. We found the single best variable. If I were willing to take all P variables and transform them into just a single column, that would be the best way to do it. But generally, we'll need more than one principal component in order to get an adequate representation of the total variability. So the second principal component, we'll call it A2 transpose X. We pick A2 such that the variance of A2 transpose X is maximized and A1 is perpendicular to A2. What we mean by that is these principal components are going in like perpendicular or orthogonal directions to one another. Each of the linear combinations is perpendicular. So if you do a dot product, A1 transpose A2, it equals 0. We're trying to discover these new variables that individually account for a lot of the story, and they do it in unique ways. We're trying to find different patterns to break our original data set up into. The biggest source of the story is the first eigenvector. Having said that, if we look in a totally different direction from that, the next best is the second principal component, which uses the second eigenvector. So the solution here is A2 equal to E2. And again, we have that the variance is the corresponding eigenvalue. So if we look at these slides again, the first principal component is the linear combination A1 transpose X that maximizes the variance. And for tidiness purposes, we're going to impose a constraint that the coefficient A1 has to have length 1. Do the EI, the eigenvectors of the covariance matrix, what's their length? 1. So suits us just fine. The second principal component is, again, a linear combination that maximizes variance subject to length 1 and subject to the perpendicular restriction. A1 and A2 need to be perpendicular to each other. That translates to uncorrelated principal components. PC1 and PC not 1 are uncorrelated. And the variance of each one of these principal components is equal to the corresponding eigenvalue. Let me show you a result, and then we'll look at a real data set. So this is slide 4, and what we have on slide 4 is that the total variance of our data, if you think of the covariance matrix capital sigma, in its diagonal elements are the variances of each of the variables. Row 1, column 1 is the variance of variable 1, and so on. So if you add up the diagonal elements, that is, in a sense, the sum, the total variance. You're adding up all the variances of the p variables. And it turns out that the sum of the variances equals the sum of the eigenvalues. That's from topic 2, I think. It's in your textbook. The sum of the diagonal of a covariance matrix equals the sum of that covariance matrix's eigenvalues. So back here, the variance of PC1 is lambda 1, and the variance of PC2 is lambda 2. One thing that tells us is that the proportion of variance that is explained by the first principal component is lambda 1 divided by the sum of all the lambdas. If the sum of the lambdas equals the total variance, then taking lambda 1 divided by the sum of the eigenvalues tells me the proportion of variance that is explained by the first principal component. And similarly, the proportion of variance that's explained by the second is lambda 2 over total variation. So, for example, if we have 10 numeric variables and I want to reduce the dimensionality for the purpose of exploring the data, suppose that the first two principal components, suppose the first one explains 60% of the variance, and the second one explains 25% of the variance. Then taken together, using just two variables, I can, quote, explain 85% of the original data set, which is a pretty big number. We could take the first and second principal component and make a scatterplot. And now we're looking at our data, our 10-dimensional data, with just a 2D scatterplot. It's not a perfect representation of the data because we're only getting like 85% of the picture. But it's a rough visual guide. And there's lots of things that we can do with the information we discover. So let me go to the data set we saw in the lecture video. That was the Hall of Fame data. Let me open these up. So here's the baseball data I was mentioning. We have for a bunch of players. These are people who played at some point in Major League Baseball, the main U.S. professional baseball league. We have their first season that they played, their last season, total number of seasons played, a categorical variable that tells us which position they played, percentage of seasons that they made the All-Star game, and then a bunch of numeric variables, how many games, how many at-bats, how many runs, hits, doubles, triples, home runs, and so on. Also, we have an indicator of whether each player was inducted into the Hall of Fame. So if you're an awesome professional baseball player and you have an awesome career, after you retire, you may be voted into this Hall of Fame. It's a very select, honor. Eventually, when we get to predictive modeling, like data mining, machine learning, statistical learning, supervised learning, we're going to play prediction exercises with this data set. If I give you the hits, the home runs, the RBIs, and all these predictor variables, can you predict whether a player is in the Hall of Fame? For now, let's just think of these as a collection of variables. Principal components is for numeric variables. So we could pick a few of these numeric variables, we have plenty to play with, and try to explain them with a smaller number of variables. Let me open up the script. hof.r. Okay. So this is the hof.r script from eCampus. And what I'm going to do is load in the data and then show you PCA, Principal Component Analysis. Data, okay. So read in the data. We have 1,016 players. We have 30 variables. With a data frame like this is, if you say names, it will print out the column names. These are all the variables we have. To illustrate our new toy, I'm going to pull out just 6 numeric variables. H is for hits. How many total base hits did you get over the course of your career? HR is home runs. RBIs is runs batted in. Average, slugging percentage, on-base percentage. You don't have to know a lot about baseball. All you really need to know is that each of these variables, the bigger they are, the more prolific a player you were. These are all quantifications of your offensive output. As a batter, how many times did you score? How much contribution did you make to scores? The bigger each of these variables, the better you were as an offensive player. So I'm going to create this capital X. Capital DTA that we just read in is a data frame. It has all 1,016 players. And then it has columns for everything we have. We have their names, we have Hall of Fame indicator, a bunch of numeric variables. For PCA, I need to focus on numeric variables. PCA is all about numeric variables. So here I'm getting capital X is just the columns containing the numeric variables I want. I said num vars is the names of the numeric variables I want to play with. And then X is a matrix that is just the columns of my data frame that corresponds to those variables. So if I run this, I now have just 6 variables. Here's the first so many rows. The names and Hall of Fame, all the other variables are gone. I just have hits, home runs, RBIs, average, slugging, on-base percentage. If I had a way of making a 6-dimensional scatter plot, I could represent the entire data set. The first player has 3,771 hits, 755 home runs, and so on. I would bet that every player has a unique collection of these 6 variables. I can completely explain or separate all the players if I use all 6 variables. Our goal is to represent the same collection of information to the highest extent possible using less than 6 variables. Okay. I'm just going to run this stuff here without commenting on it. We don't need this just yet, but I want to go ahead and run it. Just in case, I'll go ahead and run this. Here's principal component analysis. There are 2 functions in R that do principal components. There's one called prcomp, and there's another function called prinComp. They both do the same thing, just slightly different presentation and syntax. But let's try prcomp. What I'm going to do is say, do this thing called PCA, principal component analysis, using our 6 numeric variables. And I'll talk about this momentarily, but we're going to standardize our data before doing this. So again, I'll comment on that in a second. But for now, we're just going to do this thing called PCA on 6 numeric variables. So let's do that. Now if I just type PCA, I get the standard output. This is prcomp's standard output. And it shows us 2 pieces of information. The first is the square root of the eigenvalues. These are the standard deviations of the principal components. We took 6 numeric variables, and now we transformed them into 6 principal components. We're not going to use all 6, but we could completely represent the data if we use all 6. The way we decide how many of them to use is by looking at the variances. What is the variance of PC1? What is the variance of PC2? And specifically, what proportion of variance can be allocated to each of the PCs? So here if I say PCA, SDEV are the standard deviations. So if I say the standard deviations squared, that'll be the eigenvalues. And now let's add up, divide by the summed eigenvalues. So let's do sum of PCA, SDEV squared. This is just eigenvalue divided by the sum of the eigenvalues. These are proportions of variance explained. The first the first principal component explains 71% of the total variance. The proportion of variance explained by the first principal component is the ratio of the eigenvalue to the total variance. Remember that the sum of the eigenvalues is the same as the sum of the variances. I can use just one variable and represent greater than 2/3 of the story of the data. The second principal component, which is restricted to be uncorrelated with the first one, so it won't be near 0.7. It's going a totally different direction from the first one. But it still explains 14%. And then it starts dropping off substantially. So basically what we have found is that we can explain most of the story, 71 plus 14. We can explain 85% of all the variation in my 1016 players using just 2 variables. The other ones, the third one and fourth one and so on, the variance that is explained is relatively small. So they're relatively minor components of the whole picture. This dimension reduction stuff, a good visual to keep in mind is that of image compression. If you take a digital picture with your camera and you have it set at very high resolution, maybe your picture takes up 50 megabytes on your hard drive. But if you go into an image compression software and say save it to a lower res picture, maybe it goes to 1 megabyte. And if you open the two, they'll look an awful lot alike. If it's a picture of your cat, it's a cat in both pictures. It's just that the really high res one has more detail. But the compressed one has the essence of the full one. You can still see the cat, it's just a little fuzzy. That's kind of like what we're doing here. We have 1016 players and 6 variables for each. That's the full res picture of our data. Now we're going to compress it down to, in this case, 2 variables. It's still our data, but it's fuzzy. It's 85% of our data. So one thing I can do is decide how many principal components should I use to represent our data. In this case, I'm going to say, let's use 2. The other thing we can do, or one other thing we can do, is look at this output. Okay, so when I said PCA, enter, it showed us 2 things. One is the vector of standard deviations. That's square roots of eigenvalues. I can use those to get proportion of variance explained. The other thing it showed us is this thing called rotation, which is a poor choice of words, I think. Well, anyway, it is a matrix. When we do PCA, we get 2 pieces of information. One has to do with what variance of the PCs, which we can use to say what proportion of variance is explained by each PC. And the second is the matrix of eigenvectors. So here, this matrix, the first column is called PC1. That's an unfortunate choice of words as well, because that's not actually PC1. That's the coefficients that define PC1. PC1, the first principal component, is a linear combination of the P variables. So all I need to define that is A. What are the coefficients that we use to define the principal component? This column contains the coefficients that we should use to create PC1. So for player number 1, instead of the 6 variables that we started with, hits, home runs, and so on, what we're going to do is represent it as minus 0.42 times this player's hits, plus minus 0.42 times home runs for this player, and so on. This is the linear combination that I'm going to apply to every player. Then this is the linear combination we'll apply to get PC2. So if we took our N by P matrix of data and transformed it to do just PC1, it's going to be N by 1. I just have 1 variable now. If I go and add PC2, I'll have 2 variables. So we're talking about, in this case, taking 1016 by 6 and transforming it to 1016 by 2. 2, because I can explain 85% of the story with just 2. And then these numbers become relevant because they tell us not only have we reduced the dimensionality and forced our 6-dimensional data down to 2 dimensions, but these numbers tell us about how that was done. What is the essence of the structure that we took advantage of to go from 6 down to 1? These numbers tell us that. So let me just comment on these numbers. PC1, what is PC1 is a natural question. When we do principal component analysis, we want to reduce the dimensionality, we want to make a picture so we can visualize the data, and we want to make a statement of interpretation. What is it that makes PC1 so informative? If you look at PC1, these coefficients, they're all negative numbers close to minus 0.4. They're all really close to minus 0.4. Couple of comments. One comment is that if you multiply all those numbers by minus 1, their interpretation does not change at all. So whether it's all negative 0.4 or all positive 0.4 is irrelevant for our purposes. For the purposes of understanding what we captured, it does not matter the sign. So if you ignore the sign, we basically have 0.4 for every variable. Not exactly, but it's pretty close to 0.4 for all of them. So if you do 0.4, or a single constant, if all the coefficients are equivalent, if they're all the same, then it's like you're just doing 0.4 times hits plus 0.4 times home runs plus ... 0.4 times on-base percentage, XP. That's the same thing as 0.4 times the sum of the variables and that's basically like a straight average of the variables. So it's a weighted average. Not exactly a weighted average. It's basically a straight average. It's add up all the variables and divide by a constant. PC1, because the coefficients are all roughly the same, that tells us that the single most informative feature, the single best way to spread out the players, is just to average up their offensive career stats, which is a sensible thing if you think about it. What's the best way to take these 1,016 players and spread them out and explain them? Since all 6 of the variables are numeric and bigger numbers mean more offensive output, then if you just add them up, that gives you a very useful summary to explain them. If we took this transformation of all the players and then ordered the players based on PC1, we would see the lowest performing players and then a progression up to the highest performing players. This would rank the players in a sensible way. This kind of principal component, where the coefficients are all basically the same, is something we'll see repeatedly. It's a common feature of data sets. When you have multiple numeric variables that are correlated with each other, positively correlated, they're all measuring similar things, this is a very common outcome. That the best single variable for spreading out your individuals is an average, or we'll call it an index. It's like an index variable. So having said that, let's look at PC2. PC2 explains 14% of the data, 14% of the variance. These coefficients, the column PC2 is uncorrelated with the column PC1. If we do PCA dollar rotation, transpose the first column, matrix multiply second column, it's 0, or near as makes no difference, 0. All the PCs are uncorrelated with each other. It's like the best way you can spread the players out is to do this average, this index average. In a totally different direction, the next best thing you can do is PC2. These are the coefficients that define PC2. So if we look at these, there are some numbers that are substantially bigger in magnitude than others. 0.07 and 0.09 can arguably be ignored for the purposes of explaining. The biggest numbers by far are here, 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 and here. So what we typically do when it comes time to say what's the story behind PC2 is just ignore hits and slugging percentage. They don't really come into play so much. What does come into play is positive coefficients for home runs and RBIs and negative coefficients for batting average and on-base percentage. The linear combination that defines PC2 is, roughly speaking, 0.5 times home runs plus 0.3 times RBIs minus 0.6 times average minus 0.5 on-base percentage. The fact that some of the signs are different means that whereas PC1 is an index kind of variable, PC2 is a contrast kind of variable. PC2 is a difference between home runs and RBIs on the one hand and average and on-base percentage on the other. We're out of time right now, but I'll show you a little more about that on Wednesday. But PCs are about decomposing your data set into really informative pieces that are totally uncorrelated with each other. The first one will be the one that explains the most. The second one is the next best that's uncorrelated with the first. In the first case, we said the first PC was an index variable. So best way to spread out the players is to take basically an average of their variables. PC2 tells us something more subtle. 14% of the story is driven by this contrast. So players who are above average on home runs and RBIs, there's a subpopulation of players who are above average on home runs and RBIs, but below average on average and on-base percentage, and vice versa. Most players can be ordered by just averaging all their variables, but there's a subpopulation, 14% of the story, that is due to a difference. Players who hit lots of home runs and lots of RBIs, but who happen to have lower than average averages and on-base percentages. So having done this, on Wednesday, we'll make a picture, a scatter plot. I can make a scatter plot now because I just have two variables, two principal components. I know what proportion of variance each of them explains, and I can comment on what is the nature of each of them. 70% of the story is just an index overall average. 14% of the story is a more subtle contrast between these two types of players. All right, so we'll quit there. But I think I've said before, principal components and cluster analysis are kind of bread and butter operations, I would claim, for statistical analysis with multivariate data. Whenever I get a multivariate data set, which is pretty much every data set nowadays, a couple of the first things I do is PCA and cluster analysis. They're great ways to get a rough picture for your data and get kind of a big picture explanation of what makes your data tick. So, all right, thank you. Homework 3 is coming, and your exam grades are coming. Okay. For now, you could look through the notes a little bit. You might go through the code that I went through today, the Hall of Fame data code. Another example that you might check out is the movies data. So there's a movies.csv, and under scripts, the movies data are called box office. Yeah, I should rename this to be movies, but box office script goes with movies data set. Both of them have PCA examples in them. So it'd be good practice for you to look through the code that I have there and make sure you know what it's doing. All right, thank you. See you Wednesday.